as module 4. Now this assignment problem is a special case of transportation problem. In assignment problem, the objective is to minimize the total cost or time involved, and here we have to assign a number of resources to an equal number of activities. So the origin points and destination points are equal in case of assignment problem. Whereas in transportation problem, these 2 points, these 2 numbers need not be the same. So that's the difference between assignment problem and transportation problem. Again, another difference is in transportation problem, we know that there are different capacities at different origins, there are different demands at different destinations, and only thing is the total supply should be equal to the total demand. So that's where the transportation problem is said to be balanced. But in assignment problem, it is the demand at each of the point that will be 1, and the supply at each point that will also be equal to 1. The reason is explained in this following paragraph. Now this assignment problem is completely degenerate form of transportation problem. We know that in transportation problem we have m plus n minus 1 basic feasible solution, and if the number is exactly m plus n minus 1, we say that the transportation problem is a balanced one. Whereas in assignment problem, we assign a resource to exactly one of the activity, or we assign one origin to exactly one destination. So in this way assignment problem is done. So a row contain only one assignment, similarly a column contain only one assignment. It is just contrary to what we have in transportation problem. In transportation problem, a row or column may have more than one assignments. Okay, so in assignment problem, a row should have only one assignment. Okay, and therefore xij is the quantity that is transported from I to j in the sense of transportation problem. This xij is always equal to 1 or 0. So either this can happen or not happen. So only these 2 situations exist in the case of assignment problem. Okay, so that's why we say that the marginal values, that is the total demand or total supply, or corresponding to each origin point or each destination point must be equal to 1, because there is only one assignment in a row, and that one assignment can be 1, should be 1. So xij can only be 1 or 0. So all these things will be explained in detail while we do a particular problem. Now from the theory part, just for your understanding, these are the specialities of assignment problem. For assignment problem, number of rows should be equal to the number of columns. So in every row and in every column there is only one assignment, and this assignment problem is a completely degenerate form of a transportation problem. I shall explain this also later. The units available at each origin and units demanded at each the units available at each origin and the units demanded at each destination are all equal to 1. This means exactly one occupied cell in each row and one occupied cell in each column of the transportation table, and so only n occupied basic cells will be there. So what is required is n plus number of rows is n, number of columns is n, so n plus n minus 1, so 2n minus 1 is a requirement, but there will only be n occupied cells in the place of this 2n minus 1, and that's why why we say that it is a completely degenerate form of transportation problem. Okay, now let us see the mathematical formulation of the assignment problem. Now consider a problem. One second. Consider a problem of assignment of n resources, or this can be n workers, to n activities or n jobs, so as to minimize the overall cost or time in such a way that each resource can associate with only one job. So each resource gets associated with only one job. Okay, so the cost or effectiveness matrix is given as below. So we will be given the cost matrix. So in transportation problem also you will be given a cost matrix. So here also we are given a cost matrix. So likewise a cost matrix will be given. So at each position you can see the cost associated in moving from R1 to A1, or in making the job A1 done by the resource R1, the cost associated is C11, and so on. All the cost can be explained, and you can see this availability and requirement corresponding to each row and each column, they are all equal to 1. The cost matrix is same as that of transportation problem, except that the availability at each of the resources and requirement at each of the destinations is unity. Okay, due to the fact that assignments are made on a one-to-one basis. Assignments are made on a one-to-one basis means if we have O1 can be assigned to, say, suppose if we have O1, O2, O3, and we have D1, D2, D3. If O1 can be assigned to, O1 is assigned with D1, O1 cannot be assigned with D2 or D3. Similarly, if O2 is assigned with D3, O2 cannot be assigned with any of the other DIs, and similarly this O3 should also be assigned. So this is a one-to-one basis, and that is why the availability and resources, availability and the requirement are all restricted to 1. Now let Xij denote the assignment of ith resource to jth activity. Ith resource associated with j's activity, Xij be that assignment. This Xij is equal to 1 if the resource I is assigned to j. If this 1 is assigned with 1, this X11 is equal to 1. Okay, and 0 otherwise. Since 1 is not assigned with 2, X12 is 0. Since 1 is not assigned with 3, X13 is equal to 0. So that is how we define Xij. Okay. Now let us see the mathematical formulation of assignment problem. All these are different variations of our linear programming problem. So objective function will be a linear expression, and the constraints will also be linear equations or inequalities. So that's what the linear programming problem mean. So this assignment problem is also a special category of linear programming problem, where the objective is to minimize the total cost. The total cost is sigma double summation Cij Xij. This Xij is either 1 or 0. Subject to the constraint sigma I equal to 1 to n, Xij equal to 0. That is the sum of allotments in a row is equal to 1. Similarly, the sum of allotments in a column, sigma j equal to 1 to n, Xij is equal to the allotments in a column, that is also equal to 1. Xij is equal to 0 or 1, and this happens for all the columns and all the rows. So this is how we frame the assignment problem mathematically. Now, so this is the basis. This is a basic thing about assignment problem. So assignment problem is a linear programming problem. It is a special class of transportation problem, where the number of origins is equal to the number of destinations, and the availability are all equal to 1 corresponding to different origins or different source points, and the requirements at different destinations or different different activities, they are also equal to 1. So these are the distinguishing features of assignment problem when compared with transportation problem. Now let me take a particular question and let us solve and see how this assignment problem can be solved. Okay. So let me take the question. Now we are going to see the solution method for this assignment problem. Now there are different methods for solution of assignment problem. So as you can see, there is a number 4 associated with this Hungarian assignment method, and we prefer this method, this 4th method of assignment problem. The previous methods are a complete enumeration method, transportation method, simplex method, and this is a 4th one. And we prefer this 4th method for solving assignment problem because this is the simplest possible method. Now let us see how this can be done. This is the most efficient method for solving assignment problem. Now this is called the Hungarian algorithm. This method is called the Hungarian algorithm. Now let us deal with this Hungarian algorithm step by step. So I shall explain the algorithm with the help of this question. Now please see this question. A departmental head has 4 subordinates and 4 tasks to be performed. The subordinates differ in their efficiency and the tasks differ in their intrinsic difficulty. His estimate of the time each man would take to perform each task is given in the matrix below. Okay, so the time is given, not the cost, but the time for each subordinate to perform each of the activity is given. So the tasks are A, B, C, D. The subordinates are E, F, G, H, and the time required by the subordinate E to complete the task A is 18, and similarly the task time required for the subordinate G to complete the work C is given as 18 hours, or whatever that be, 18 units of time. 18 hours is required for completing the job C by the subordinate G, and so on. So like that, this matrix can be defined, can be explained. So how should the task be allocated? 1 to a man so as to minimize the total man hours. So that's a question. Minimization of the total man hours is the question. Now for that we are going to apply the Hungarian method, and let me explain the Hungarian method step by step. First step is determine the cost table from the given problem. So that I have already written here. This is the cost table. So we just write down the values of the values from this matrix given in the question. So this is the first step. If the number of sources is equal to the number of destinations, go to step 3. So this is the situation for us right now. Number of sources is equal to number of destinations. Otherwise, if the number of sources is not equal to the number of destinations, then go to step 2. Let us just read that step 2. When the problem is not balanced, that's what is given by this second case, add a dummy source or dummy destination so that the cost table becomes a square matrix. The cost entries or dummy source or destinations are always equal to 0. So this is similar to what we have in transportation problem in order to make it balanced. So if the number of rows is less, we add one more dummy row with all the cost equal to 0. If the number of columns is less, we add a dummy column with all the cost elements equal to 0. Okay, so in that way we can balance an assignment problem. So for us right now, the problem is already balanced, so we can just skip this step 2. So let us go to step 3. Locate the smallest element. Locate the smallest element in each row of the given cost matrix, and then subtract the same from each element of that row. So let us take the first row. We locate the smallest element is 11, and subtract this 11 from each of the elements of this particular row. So 18 minus 11, then we have 26 minus 11, then we have 17 minus 11, then we have 11 minus 11. Now for the second row, the minimum value is 13, and we are going to subtract this 13 from every other element of the row. So the second element is 15, the third element is 1, the last element is 13. So by taking the difference between the other elements and 13, we have the modified second row. Now for the third row, the minimum element is 15, and we subtract 15 from every other element. So 38 minus 23, 38 minus 15, 19 minus 15, 18 minus 15, and then 15 minus 15. And for the last row, minimum value is 10. So we subtract 10 from every other element. So 9, then 16, then 14, and then 0. So we covered the step 3. We identified the minimum element of each row and subtracted it from every other element of the row. So we completed step 3. Now let us go to step 4. Let us identify step 4. In step 4, in step 4, if the in the reduced matrix obtained in step 3, so this is step 3, this is what we have in step 3. In the reduced matrix obtained in step 3, locate the smallest element of each column and then subtract the same from each element of that column. So just as we did for each row, we have to do for each column. So hence let us take column by column. First column, minimum is 0. So when 0 is subtracted from every other element, we have that first column itself, no change, 7, 0, 23 and 9. Then for the second column, the minimum value is 4. So we have to subtract 4 from every other element. So 11, then 0, then 12. Then for the third row column, 1 is the smallest element, so we subtract 1 from every other element. So 5, 0, then 2, then 13. Then for the last row, 0 is the smallest element, so the last column remains the same. So 0, 13, 0, 0. So now that we have completed step 4. Now we go to step 5. So this is step 4. This is step 4. Now we go to step 5. In the modified matrix obtained in step 4, search for an optimal assignment as follows. So we search for an optimal assignment. See what is to be done. Examine the rows successively. Examine the rows successively until a row with a single 0 is found. Enrectangle this 0 and cross off all other zeros in its column. Continue in this manner until all the rows have been taken care of. So let us see what can be done here. Examine the rows successively until a row with a single 0 is found. So we check the rows one by one, starting with the first row. So in the first row itself, we can find only one 0. So the first row, it's with a single 0. So we rectangle that 0 and then cross off all the other zeros in this column. So we have to cross off all the other zeros in this column. Okay, then we go for the next row. Since there is more than one 0, we just skip that 0. So we are asked to find a row with a single 0. So since the second row contains more than one 0, so we just skip that second row. Now when it comes to the third row, even though it had two zeros, one 0 is already cut off. Now the row is left with one 0. So we choose that 0. Okay, and then cut off all the remaining zeros in that particular column. But for this particular column, there are no zeros, only one 0 was there, and so we don't have to change anything. Now coming to the last row, there is no 0 in the last row. So we completed this step 5A. Now repeat the procedure for each column of the reduced matrix. So this is a reduced matrix. So we are applied step 5A part. Now let us repeat the same procedure for columns of this reduced matrix. Now for the first column, there is only one 0. So we rectangle this 0 and then we cut off the remaining zeros in that particular row. For the second column, it is already a rectangle. For the third column, no 0 remains, and for the fourth column also, there is already an assignment made. Okay, so we completed step 5A and B. Okay, then C is already discussed. D is repetition of this procedure again and again till all the possible assignments are made, and also what you have to notice is at the end of the step 5, all the zeros must be either in rectangle or they should be cut off. So either all the zeros should be put within that rectangle or it should be cut off. So no zero should be left without any of these two operations. So that's one thing that you have to notice after completing step 5. Okay, so we have completed step 5. Now let us go to step 6. So we are doing step 6 now. See, if the number of assignments is equal to n, here the number of assignments n is equal to number of assignments is equal to 3. It is not equal to n. Number of assignments is not equal to n. So if the number of assignments is equal to the order of the matrix, the optimum solution is reached. But unfortunately, we haven't reached the optimum solution. So we have to go to the next step. Step 7. Draw the minimum number of horizontal or vertical lines to cover all the zeros of the reduced matrix. This can be conveniently done by a simple procedure. So let us try to understand this simple procedure. So here the number of assignments is not equal to the order of the matrix, so we have to improve the current solution. Now in order to improve the current solution, we have to draw minimum number of horizontal and vertical lines so as to cover the whole number of zeros. So in order to draw a number of horizontal or vertical lines, we are going to follow a procedure that is given in step 7. So let us try to see what that is. One second. Okay, now let me read this step 7 and simultaneously we can apply that step 7. See, step 7a is mark rows that do not have any assigned zero. Mark rows for which there is no assigned zero. See, for the first row there is an assigned zero. For the second row there is an assigned zero here. There is an assigned zero. Assigned zero means the zero that is put within that rectangle. That is called the assigned zero. So there is an assigned zero for the first row. There is an assigned zero for the second row. There is an assigned zero for the third row. But for the fourth row, there is no assigned zero. So we are asked to mark the row that do not have any assigned zero. So the first row has an assigned zero, the second row has an assigned zero, and the third row has an assigned zero, but the fourth row do not have an assigned zero. So we mark tick for this fourth row. Okay, then mark the column that have zeros in the marked rows. Now we look for, so tick marked rows are otherwise called marked rows. Now we check this marked row. So we check the marked row and we check in this marked row. So we are now bothered only about this last row. So in this last row, check whether there is any column that has zeros in the marked row. For this marked row, check whether there is any column with zeros. So this last column has zeros. So we mark that particular column. Okay. Then we look for this column which is marked now. Now in this column, we check whether there are any rows with marked zeros. So in this tick marked column, we look for any row with marked zero. Now actually in this tick marked column, there are two zeros. So one in row 3 and one in row 1. But only the zero in row 1 is has an assignment. Hence, this row 1 is chosen and hence we tick mark the row 1. Is it clear? Let me repeat it. See, first marking. So let me repeat the whole process once again. See, mark the rows that do not have any assigned zero. So the first row has an assigned zero. Assignment in the assignment is otherwise rectangling the zero within this rectangling that zero. That's what's called assigned zero. So the first row has an assigned zero, second row has an assigned zero, third row also has an assigned zero. Only the row without any assigned zero is fourth row, and so we mark the fourth row. Okay, now we consider only the fourth row. In the fourth row, we check whether there is any column that have zero. We are not asked to find the marked zeros, but column with zeros in the marked row. So we consider the fourth row and we check whether there is any column with zero. So the fourth column do not have any zero. Okay, fourth row has zeros. So fourth column has zeros. So we choose this fourth column and we mark this fourth column. Now we find this marked column and we check whether there is any assigned zero in this marked column. Yes, there is one assigned zero in the marked column, and that is in row 1, and hence we mark that first row. Now go through this first row and see whether there is any 0 in that first row. See, mark the columns that you have zeros in the marked row, that is over. Then mark rows that have assigned zeros in the marked column. So we mark the row 1, and then again we have to repeat B. Repeat B means mark columns that have zeros in the marked row. So we do not have a column with 0 in the marked row. We do not have a column with 0 in the marked row. So hence this marking is complete right now. So hence we have completed all the marking. So if there were some 0 in this first row, we should have continued this marking. But for the time being, there is no further marking for this particular matrix, and therefore we are going to see this E. See what is to be done here. In E, what is to be done is draw the lines through all the unmarked rows. Draw lines through all unmarked rows. Marking is putting this tick mark. So draw lines through all unmarked rows. So let me draw a line between the unmarked row. So this second row is an unmarked row. So let me call it as L1. Then again third row is an unmarked row. So third row is an unmarked row. So let me mark it as L2. Then draw line through marked columns, unmarked row and marked columns. So the marked column, there is only one marked column, and that is the last column, and so this is our, so let me call this as L3. So you can see that there are only 3 lines. If the minimum number of lines is equal to the order of the matrix, the procedure would have completed in this stage itself. Then even before proceeding to this step 4, we would have finished the entire procedure. Okay, so now we have only 3 lines. Now what we are going to do is, we are going to revise this matrix. Now let us see how that can be done. That is explained in step 8. Find the smallest element of the reduced matrix not covered by any of the lines. Find the smallest element of the reduced matrix not covered by any of the lines. I'm sorry, this line is not straight. Okay, so this is our L2. Okay, we have to identify the smallest among the numbers that are not covered by any of these lines. Okay, now the smallest among the values 7, 11, 5, 9, 12 and 13 are the uncovered elements, the elements that are not covered by the straight lines L1, L2, L3. Now the minimum among these is 5. So in next stage we are going to subtract this 5 from all the uncovered elements. Then the covered elements remain the same, but the junction elements will be changed. Junction elements will be added with this small number. So let us see what happens. Let us modify this matrix. First element is 7. 7 minus 5 is 2. Second element is 11. 11 minus 5 is 6. Third element is 5. 5 minus 5, it is 0. Then see, the last element 0 is covered by the straight line. It has no change. Then for the second row, first element, it is covered by the line. It has no change. Second element is also covered. Third element is also covered. No change. But to this last element, it is actually a junction element in the junction of L1 and L3. So the junction element gets changed, and that will be added with the smallest element. So 13 plus 5, that is 18. Now the 23 remains the same. Then 0. Then 2. Then 0 plus 5, that's 0. This 0 is also a junction element, hence that also gets added by this 5. Then 9 minus 5, 9, 12, 13 are uncovered elements, so 9 minus 5, then 12 minus 5, 13 minus 5, then 0 remains unaltered. So in this way we modify the matrix that is given in the previous stage, and this is step 8. Okay. Now we repeat step 6. What is step 6? we repeat the step 6. Even before repeating this step 6, we find the smallest element not covered by any of the lines, so that is already done. Subtract this element from all the uncovered elements and add the same to all elements lying at the intersection of the two lines, so that is already done. Now go to step 6 and repeat the procedure until an optimum solution is obtained. So let us see what that step 6 is. So this is step 6. Let us see, that is going to be repeated. If the number of assignments is equal to n, an optimum solution is reached. So we have to see whether there is an optimum solution or not. So how to identify that optimum allocation? Now in order to do that optimum allocation, we have to actually do with the n rectangling of the single row in each, the single zero in each row. So we have to actually do step 5. Let us see how that can be done. Now consider this matrix in step 8. Consider the matrix in step 8. First row has 2 zeros. We can't do anything with the first row. Second row also has more than 1 zero. We cannot have done anything. But the third row contains exactly 1 zero. Third row exactly contains 1 zero. So we consider this a 0 in the third row. We n rectangle it, and if there are any zeros in the corresponding column, we have to cut it off. Since there is no zero in this corresponding column, we don't have to do anything. Coming to the last row, exactly there is 1 0 there, so we have to n rectangle it and we have to cut off the remaining zeros in that column. So all the rows have been taken care of. Now column by column, the first column has only 1 0, so we have to cut off the remaining zeros in that particular row. Then for the second row, second column, it's already done. For the third column, there is only 1 0 remaining. So we n rectangle that 0, and all the other zeros in the particular row are already cut off, so we don't have to do anything. So we made the optimum assignment. So now the assignment is optimum. Why is it so? Because because the number of assignments here, the number of assignments is equal to the number of assignments. Assignments are done with respect to the help of rectangles. So number of assignments is 4, that is equal to the order of the matrix. So now the solution is over. We have completed the whole procedure and we reached the optimum solution. Now let us just read this optimum solution. Let us see how this optimum solution can be read. See, this is A, B, C, D, and this is E, F, G, H. Okay, so we have A to G, then we have B to E, then we have C to F, and then we have D to H. That means there is exactly one allocation in every row and there is only one allocation in every column. So that means the person G is entrusted with the task A, the person E is entrusted with task B, the person F is entrusted with task C, and the person H is entrusted with task D. So this is the optimum allotment. This is the optimum allotment that can be done for this particular question. And the solution, the last solution part should read the minimum time for completing this assignment from A to G. From A to G, the time given is 17 man hours. Then from B to E, the time given is from A to G, the number of man hours is 17. From B to E, it is 13. Then from C to F, it is 19, and from D to G, it is 10. So adding all these, we have the total time as equal to 59. So 59 man hours is required to complete the entire task. So that is the answer to the first question.